All right, so what we're going to do is we're going to pick up right where we left off with electron configurations. I'll kind of rewind just a little bit and go back through the chart, the mnemonic chart that helps you remember the order of the orbital energies. I'll go back through and redraw energy orbital diagram, but remember that energy orbital diagrams and electron configurations are closely related, and they have exactly the same information, but one is more a visual representation and the other one is more of a textual representation. Well, that's visual too, but they really are two different types of questions. So someone may say, draw an energy orbital diagram, and then you want to draw the picture. Someone may say, what's the electron configuration? And then you just write it out. So we'll start from there. We'll rewind a little bit, and then we'll move in with kind of filling in the gaps with electron configurations, and then we'll move into the periodic trends, and then it'll be it for the day. It's going to be a short session. Okay, let's rock on this. Let's get this going. Let me throw up the whiteboard. I love to come into introductory chemistry, starting with the screen of Organic Chemistry 2, get you guys nice and terrified. Then I erase it and you feel better, right? Yeah. Okay, so let's take a look. Let's start off with kind of a reminder of what electron configurations are. And this will be my energy orbital diagram. These things they tell the reader what atomic orbitals are populated with electrons. Now, here's this mnemonic, and the mnemonic helps you remember the energy order. And with one bit of caveat, this thing that is presented to you in different ways. I present it this way because this is the way that I've been doing it since I was essentially your age. In other words, when I was in my first chemistry class. You can draw this mnemonic in other ways, and I think the book does present it differently than I do, but either way is okay. The bottom line is that to remember that for each principal quantum number, and remember the principal quantum number is this n value. For each principal quantum number, the subshell type increases. So for each principal quantum number, you get access to a new subshell type. So in the one principal level, the one quantum level, you only have access to s orbitals, but in the 2 quantum level, you get access to p orbitals. In the 3 quantum level, you get access to s, p, but now you get access to d. At the 4 quantum level, you get s, p, d, but now you have access to f as well. By the time you get to the 5 quantum level, you really are starting to get a lot of electrons represented. You get access to d, you get access to f, and Oh, you know, I switched it from 4 to 5 to 4. Let's try that again. But now you get access to G, and this is where things go alphabetically. So it's, you have to remember that it's S, P, D, F, and then everything happens alphabetically. Each letter corresponds to the subshell type. And remember, what I mean by subshell type is, I mean, what's the shape of the orbital? You have to know the shape of SP and D. I showed you the shape of F, but you don't have to know it. I didn't show you the shape of G, and you don't have to know it. But it is spherical for S. That's right, Shaq. It's hard for me to draw a sphere, but if I put a little shiny spot on it, then you can see that it's a sphere. You'll see two-dimensional projections of these orbitals in pictures on quizzes and exams, and the pictures will be much better represented than my incredibly poor artistic skills can develop online. Here's what I'll do real quick, just to make sure that everybody's good. Let me switch over, and I will share my screen, and I'll show you some pictures of atomic orbitals. Okay. Ignore that. I don't know where this came from. That's interesting. Here they are. Here's a decent representation of what the atomic orbitals look like. The top of the pyramid, they do have shapes. They do have shapes, but they don't have shapes that you have to know, okay? Because let's take a look at F for on this chart. You do have to recognize S orbitals, P orbitals, and D orbitals. But you don't have to recognize F orbitals. And look at what's going on. They look similar, right? They're, as we continue to go up from S to P to D to F, you're essentially, one way to say it is you're adding lobes. S has just one spherical shape, but now when we're at P, there's 2 lobes. And when we're at D, there's 4 lobes, except for the one in the middle. It's got the donut and the dumbbell shape. When we move to F, you're getting orbitals that have more nodes, or more lobes, excuse me, except for the donut dumbbell shape, but then it just gets more donuts. And so I don't expect you to be able to recognize an F orbital or a G orbital, but in general, this pattern continues to increase, right? You continue to just add lobes. It gets more compact, more busy. There's a lot more stuff that's going on, but you don't have to know them. But here's a decent picture, a decent diagram of what you might see on a quiz or an exam. So if I just show you this shape where my cursor is circling, and I don't include any of this designation down here where it says P, I would say, what kind of orbital is this? And you would say, that's a P orbital. I might show you this shape here, the D orbital in the middle, and say, what kind of orbital is that? And you would say that it's a D orbital. So the question was asked earlier, what does each letter mean? And each letter corresponds to each orbital type. But when we're doing electron configurations, we don't really need to have the shape of the orbitals handy. It doesn't really it doesn't really have anything to do with that. It just means the volume of space. The question is asked, if there's more loaves, is that the heavier the element? You could say that it's a heavier element because it has electrons populated in higher energy orbitals, thus it has more electrons, thus it's going to be one of the heavier elements. But it's not directly related to that. It's just that as we increase the quantum values of the allowed electron states, the types of orbitals become more complex that those electrons exist in. And so when I get back to this mnemonic chart that helps us remember the orders, what I was saying is that you're starting, even once you've got into 4s and 5s, principal quantum level 4 and 5, you really are starting to represent quite a lot of electrons. And even though this chart theoretically increases or continues into infinity, there's only about 100 or so elements. And so even if you wanted to write the electron configuration of some of the heaviest elements, you wouldn't need a lot of atomic orbitals past the 7 principal quantum level. And that is because, remember, and as you just saw on that chart, that there's actually 3 p orbitals, there's 5 d orbitals, there's 7 f orbitals, and there's 9 g orbitals. And each orbital can hold 2 electrons. So at the 5d level, there's 10 electrons that go there. And in fact, at all d levels, you can do 10 electrons. So just 4d, 5d, and 3d, that's 30 electrons total. And so it doesn't take long until you've really represented quite a lot of electrons. All right, so what I will do is I will just draw one extra level, 6s, 6p, 6d, 6f, 6g, 6h, and remember that it continues to go up. You draw arrows up on the diagonal to help you remember the order. And that is because after you get to 3s, it doesn't go 3s, 3p, then 3d in energy level. It goes 3s, 3p, then 4s, then 3d. And that's why we use these arrows. And I'll draw one last arrow because I just want to remind everybody there's something that I didn't write there, but that the arrow does go through. And if you ever get up that far in your chart, or maybe you don't write the 5 level or the 6 level, you'll have to remember that the 7s level is still there. Okay, and so let's go down with our energy orbital diagram. So I'm going to place an energy axis on it, and I'm going to start to draw each electron or atomic orbital energy level. So that's 1s. Why did I put 1 dash there? 1 spot for electrons. Some charts will show this in a box. I don't use a box because then it confines my arrows. I just use a line to represent the place. Why did I put just 1 line there to represent 1 place? Get myself some more coffee. Right, there's 2 electrons per orbital, but why didn't I do this? Put 2 orbitals there for 1s. Yes, the S series has only 1 orbital. That's right, Maddie. 1s, 2s, then 2p, 1, 2, 3. Remember that for the p series, there's 3 orbitals. Yeah, that's what I'm asking. You got it. Then what's next? 2p, then 3s. Remember, for any s series, there's only one. Then 3p. What's after 3p? 4s. Then 3d. For 3d, there's 5. And then I'll do one more. I'll do 4p. Okay. So let's just think about how many electrons now. Yeah, 5 for D. How many? 1, 2, 3, 4, 5. How many electrons that we've represented just by getting to the 4p level? I can do 2 electrons here, 2 here, 6 here, 2 here, 6 here, 2, 5, and 6. So what is that? 4 plus 6 is 10, plus 2 is 12, plus 6 is 18, plus another 2 is 20. Now I'm at 25. Now I'm at 26 electrons. So actually I did the math wrong, didn't I? 2, 4, 10, 12, plus another 6, that's 18, plus 2, that's 20. We're at 20 once we get here. Then we've got 5, that's not 5 electrons, that's 10 electrons. So we go from 20 to 30 electrons. And then up here we're at 36 electrons. So that's quite a lot of electrons just at the 4p level. So you're already at 36 at 4p. Yeah. What? Thanks. Thanks for correcting me. I didn't see your correction but I corrected it myself. I did it all by myself. All right, so here's my energy orbital diagram. All right, so if we're at 4p and we have 36, then we get to 5s, that's 32. Then 4d, we'll add another 10. Now we're at 42. So you can see by the time we get to 4f, we're really way up there in the periodic table. That's why you don't really ever get in here and you don't need these orbitals, 6g and whatnot. Okay. And so let's take a look at some electron configurations. Let's just start over again with carbon. How many electrons does carbon have? It has 6 electrons. So the electron configuration is 1s2. I can put 2 electrons there. 2s2. I can populate 2 electrons. That's 4. So I need 2 more electrons in the next level. The next level is 2p. So I can put 2 electrons there. As I go up the periodic table, I add, nitrogen. I add 1 extra electron for every 1 extra atom, or 1 extra proton. So I'm not going to do this for every atom, but I do want to illustrate nitrogen, oxygen, fluorine, and then finally neon. Okay. And how would I represent this in the orbital diagram? I do it visually, and I fill them in 1 arrow at a time, up first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for neon. remember to fill in up arrows first whenever there's multiple orbitals at a particular energy level. It's called, I don't even want to say that the rule's name is the Hund's rule, but you don't have to remember that name. But that's, and even in general chemistry, we use the phrase, we say that it's a rule rather than to tell you why. So we don't even tell you why until physical chemistry. Okay, so let's do one more then. Let's do phosphorus. What's phosphorus? It has 15 electrons. So 1s2, 2s2, that's 4. 2p6, how many was that again? 10. Then we're at 3s. We're at 12. And then what's after 3s? 3p. And it has 15, so that was 12. I need 3 more, so it's 3p3. So if I were to fill in the electrons, I got all the same ones that I filled in up here. Got all of these. They're the same. Then 3s, then 3p1, 2, 3. Okay. So there's a couple of things that I want to introduce now. I want to introduce the first thing I want to introduce is a type of shortcut. Notice neon, and remember that neon is a noble gas. Notice the electron configuration for neon. 1s2, 2s2, 2p6. Notice that that electron configuration is right there. So because chemists are lazy, and when we get to electron configurations of larger atoms, they really do start to get pretty long and tedious to write out. So we came up with something called the noble gas shorthand. The noble gas shorthand. And that basically is to say that when writing electron configurations, it's okay to tell the reader, hey, look, here's all of the electron configuration of neon that precedes the rest of the electron configuration for phosphorus. Because neon's electron configuration is buried in phosphorus, we use this shorthand to tell the reader that, hey, the electron configuration before 3s2, 3p3 is the same as neon. And so we call it the noble gas shorthand because the noble gases are at the end of each row on the periodic table. And so once you've moved into the next row, you can use the noble gas shorthand. So for instance, if I were to go with potassium, potassium has 19, so it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's potassium. If I were to do the electron configuration of argon, I would see 1s2, 2s2, 2p6, 3s2, 3p6. And so the electron configuration of argon is right there for potassium. And so I say to myself, it's okay. I'm going to erase this right here. It's okay to say that the electron configuration for potassium is argon 4s1. So this is what I mean by the noble gas shorthand. Now there isn't a shorthand in the energy orbital diagram because you're drawing a picture of all the electrons and the orbitals that populate them, or that they're populated in. But you see it often in the electron configuration part. Okay. All right, so I'm actually gonna erase the mnemonic now because I don't think we need it anymore. We don't need it anymore for the discussion. You should have it written down on a piece of paper, and you need to be able to reproduce it out of your head. So you're not going to be given that chart on an exam or quiz. You need to be able to reproduce it in your mind. All right, so that's the noble gas shorthand. I want to then introduce a definition. The valence electron. This is an electron. I'm going to define it two ways. The first way I'm going to define it is sort of a description. It's electrons in the outermost shells of atomic orbitals. Now I'm going to be real specific. They're electrons populating orbitals with the largest principal quantum number value. So from a qualitative sense, from a general sense, valence electrons are the outermost electrons in any atom. Specifically, they are the electrons populating orbitals that have the largest principal quantum number value. So let's take a look at what I mean by that. Let's go back and look at carbon. Carbon has an electron configuration of 1s2, 2s2, 2p2. So what are the principal quantum number values in the electron configuration of carbon? You've got some 1s and you've got some 2s. All right, so I'm going to ask you a really tough question now. Which one of those numbers is larger? Give up? It's 2. So what are the valence electrons in carbon? Well, there are any electrons populating the orbitals with the largest principal quantum number. So the 2s2 and 2p2 electrons are the ones that are considered the valence electrons. They're the electrons in the outermost part of the atomic orbitals for carbon. So what about nitrogen? Same thing here, right? Here are the valence electrons for nitrogen. But once we get into phosphorus, I'm going to erase these shorthands as well. You know that you can do that if you want, that's fine. I need some room. Once we get into phosphorus, we have 1s, 2s, and 3s. So I'm really going to ratchet up the difficulty here. Which one of those numbers is larger? Do you give up? Somebody knows. Yep, 3. So the valence electrons for phosphorus are these. So I'm going to ask you questions like, what are the valence electrons? How many valence electrons does phosphorus have? How many? That's right. The answer is 5 valence electrons. That's right. Exactly. How many valence electrons does potassium have? How many valence electrons does potassium have? It's not 7. It's 1, exactly. Because now I choose 1, 2, 3, or 4. Well, I think by now we've remembered our grade school numbering and that 4 is the largest out of all those those 4 numbers. And so there's the valence electrons. So potassium has 1 valence electron. How many valence electrons does argon have? $88. Yeah, 8. 8. Okay, what I want to do is real quick is I want to pause there. I want to switch over to sharing my screen on the computer. I want to pull up a periodic table of elements. And some periodic tables you'll see will have electron configurations. And so let's see if I can find one that does. Well, this one's really hard to see. So let me blow up. Let's take a look. You might be able to see underneath the name, it's going to be really kind of starting to be almost, you can't see it. But underneath hydrogen, you should see a little 1s1. Okay. These are the electron configurations of these elements. Well, what's the electron configuration for helium? It's got 2 electrons, so it's 1s2. Let's take a look at lithium. Look how it's already used the noble gas electron configuration. It's got helium and then 2s1. The other thing that I'd like you to notice is that as you move across the periodic table, we're just adding an extra electron into each of these different orbitals. So by the time we get over here to neon, we're at helium. I don't know if you can see it. I'm hoping you can. I can see it on my screen. Helium 2s2, 2p6. Fluorine 2s2, 2p5. Oxygen 2s2, 2p4. Nitrogen 2s2, 2p3. So going the other direction, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. We're just adding an extra electron because that's each successive atom has 1 more electron. Okay, let's think about the valence electrons. What you're seeing here is the valence electrons orbitals listed. So 1s1, hydrogen has 1 valence electron. Let's go back up to potassium. Potassium's electron configuration was argon 4s1. It has 1 valence electron. Well, look at sodium. Its electron configuration is neon 3s1. Lithium, its electron configuration is helium 2s1. Do you see a pattern here? How many valence electrons does everything in group 1 have? Yeah, the pattern is by groups, right? How many valence electrons does everything in group 1 have? Yeah, it has 1. Everything in group 1 has 1 valence electron. Now, I'm going to tell you that the definition of what a valence electron is for transition metals changes. And so we don't really think about how many valence electrons a transition metal has until we get into junior level inorganic chemistry. After you've taken general chemistry, organic chemistry, and analytical chemistry, then we can take inorganic chemistry, and we can think about what the valence electrons mean for transition metals. At this level of chemistry, we don't even think about it. So we just say, let's take a look at group number 2. How many valence electrons does group number 2 have? Yeah, look at everything in group number 2. 2. Let's skip the transition metals and let's go over here and look at group 13. How many valence electrons do the atoms in group 13 have? How many are here? 3. 3. How many valence electrons in the 4s system? Or the 4 system, the 4 quantum number system. Even with gallium and indium and thallium, you're talking about 3 valence electrons. What about group 14? Right, 4. What about group 15? 5. What about group 16? 6. Yep. Group 17. 7. Group 18. 8. So I hope you see the pattern now. And so you know the definition of valence electrons, but I want you to be able to use the periodic table in order to identify the number of valence electrons an atom has just by its position without having to really think about its electron configuration. And so let's review. Group 1, 1 valence electron. Group 2, 2 valence electrons. Skip the transition metals. Group 3, 3 valence electrons. Group 13, excuse me, 3 valence electrons. Group 14, 4. Group 15, 5. Group 16, 6. Group 17, 7. Group 18, 8. The pattern is similar to the pattern that the ions take. Okay. With that being said, let's go back and look at those ions. Let's go back and look at those ions. Okay. Let's consider phosphorus and some associated electron configuration. So it was 2p6, 3s2, 3p3. All right. Well, let's take a look at what's next to phosphorus. Let's do sulfur. What's sulfur? It has 1 extra electron, so 2s2, 2p6, 3s2, 3p4. Let's look at chlorine. 1s2, 2s2, 2p6, 3s2, 3p5. Let's take a look at argon. 1s2, 2s2, 2p6, 3s2, 3p6. Let's take a look at potassium and calcium as well. I want to erase this definition over here. Give myself some more room. So let's look at potassium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and finally calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Ooh, lots of writing. You see that my handwriting got sloppier as we went. All right, let's take a look. Let's think about these ions. I told you that the pattern of the number of valence electrons is similar to the pattern of the ions, and there's a reason for that. What is the formula for the phosphide ion? What is the formula for the phosphide ion? That's phosphite. That's phosphite. So I'm thinking specifically of phosphide. That's phosphate. PO4, 3 minus, is phosphate. And Majan, that's not, and you guys, nobody's actually, I want to make sure that everybody's on the same page. Nobody has yet listed a correct formula for any ion. So remember, phosphate, PO4, 3 minus. Phosphite, PO3, 3 minus. Oh, PO3, 3 minus. Phosphide is P. Three minus. P, 3 minus. Somebody's going to have to study up on their nomenclature before the final exam. Okay. What about sulfide? What's the formula for sulfide? Right, S2 minus. What is the formula for chloride? What is the formula for potassium ion? Yep, K plus. Potassium ion is a positive ion. What is the formula for calcium ion? Okay, so let's review. Did calcium lose electrons or gain electrons to become calcium ion? Right, it lost electrons. Did sulfide gain electrons or lose electrons to become sulfide? All right, so how many electrons did calcium lose to become a calcium ion? How many electrons did sulfide gain to become sulfide? 2. Okay, everybody's starting to get on the same page. So that affects their electron configuration. If phosphorus gains 3 electrons to become phosphide, sulfur gains 2 electrons to become sulfide, chlorine gains 1 electron to become chloride, Potassium loses an electron. Calcium loses 2 electrons. Let me erase these. These are not part of the electron configuration. I'm just telling us how many electrons we lose and gain here. That will change the number of electrons in the electron configuration. So how does this work? What's the electron configuration for calcium ion if it lost 2 electrons? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. It loses those 2 electrons. Calcium or potassium ion, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. It loses that 1 electron. Phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. It gained 3 electrons to become 3p6. Sulfide, 1s2, 2s2, 2p6, 3s2, 3p4. It gains 2 electrons to become 3p6. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. It gains 1 electron to become chloride, 3p6. This is all the same electron configuration as argon. There's something to be said about the noble gas electron configurations. A full subshell is stable. The reason that the atoms gain the numbers or lose the numbers of electrons they do, for instance, if I'm calcium, I lose those 2 electrons because a full p subshell happens to be a very stable electron configuration. The reason these ions take on the charges that they do is because they are approaching a noble gas electron configuration, because that electron configuration is stable. That's why there's a pattern in the periodic table, not only for the number of valence electrons, but for the charges that the atoms take when they become charged. What is the word? What is the word that we use to describe these electron configurations? They are isoelectronic. Iso means the same. Electronic refers to the electron configuration. The same electron configuration between 2 chemical species. Okay. All right, any questions about that? I want to pause real quick. Okay, so the last little bits in this section is periodic trends. One of the consequences of having electrons is that, and you have patterns of electrons, is that you have patterns in the periodic table. We've already seen one of the patterns. Here's my quick and dirty periodic table. You've seen one of the patterns, which is how the atoms change and gain and lose electrons in order to become ions. There's 3 different patterns that you have to know in this course. And what I do in order to show you these patterns is I draw this periodic table, and we think about it in terms of directions. And so the atomic size increases this way. Oh, no, I'm sorry. That makes no sense. It increases this way, and it increases this way. If I were to draw one arrow, I would say that on the diagonal, it increases in general this way. Now, there is a reason. Even though I'm adding more electrons as I go this way, the atom gets smaller. Even though I'm adding more electrons from there to there, the atom gets smaller. The reason is beyond this course. We do tell you the reason in general chemistry, and I will write it down so those of you who are interested can look it up. It's the effective nuclear charge. This is why it gets smaller. Size. What does size mean? I literally mean the size of the atom. And so we have up till this point looked at atoms like little balls. Now what we need to do is become a little bit more sophisticated and realize that one atom is bigger than another atom. And there's a pattern of how that happens on the periodic table. You can predict that pattern. Oxygen is smaller than nitrogen. Oxygen on the periodic table is here. Nitrogen on the periodic table is there. So if I'm going this way in a row, the atoms are getting larger. So nitrogen smaller than oxygen. Nope, hydrogen is not the largest, right? Because as I go down the rows, I'm getting bigger. So hydrogen is smaller than lithium, which is smaller than sodium, which is smaller than potassium, which is smaller than rubidium, which is smaller than cesium. Wait, did I draw the positions of the atoms wrong? I sure did. Let me go back here and redo this. Nitrogen is here. Oxygen is here. So nitrogen larger than oxygen. So the question is asked, are we sure that it doesn't get bigger this way? I'm absolutely positive. This is counterintuitive. It is counterintuitive because oxygen has more electrons than nitrogen. Well, if I'm adding more electrons, doesn't that mean I'm getting the atom is getting bigger? The answer is no, it's not. And the reason is, again, beyond this course, but if you want to look up why that actually happens that way, then you need to understand the effective nuclear charge. Suffice it in this course to say that as you move from left to right in a row, atoms are getting smaller. That's why I drew the arrow this way, because as you move from right to left, the atoms are getting bigger. As you move from the top to the bottom of the periodic table, the atoms are getting bigger as well. And so if I were to draw one arrow on the diagonal that represents both this one and this one, the arrow would be like this. Yeah, so I mean, when our periodic table, francium would be the largest atom. Everybody okay? Dr. Romero, are you all right? Stay with me after the class and I'll explain that to you a little bit more. Okay, here's another trend that you need to know. Ionization energy. At this point in the course, you understand that chemical processes require energy. The value that this energy takes also has a pattern on the periodic table. So as we go across a row, the ionization energy goes up. And as we go from the bottom to the top, the ionization energy goes up. So if I were to draw a single arrow to represent the pattern, the trend in ionization energy looks like this. So what has a higher ionization energy? Germanium or fluorine? Which one has a higher ionization energy? Germanium or fluorine? Yeah, germanium is here. Let's do that again. Germanium is here and fluorine is there. So fluorine has a higher ionization energy. And that makes sense to us in a way. We can describe it this way. It makes sense to us because what's happening in the formation, what happens throughout the process that is ionization? In our language, ionization means becoming a cation. So does fluorine become cations? Is that what it prefers to do? If fluorine is going to become an ion, what does it do? It becomes an anion. So fluorine doesn't want to give up electrons, it wants to gain electrons. So doesn't that make sense that it takes more energy to get rid of an electron in fluorine than it does in germanium? one last trend that you have to know. This one is metallic character. This is what the properties of metals. This is how the periodic table, how the atoms on the periodic table go from less metallic to more metallic. And this one you should already know, right? Because what are these over here on the periodic table? What are these called? Come on, guys. We know this. Those are the non-metals, right? Then what happens over here? I get non-metals to metalloids. And then what are these things over here called? Those are all sorts of different metals. I've got transition metals, I've got alkali earth metals, and I've got alkaline metals over here. So all of this stuff on the left side are metals. All the stuff on the right side are non-metals. So it's no surprise that the metallic character of atoms increases towards the metals. So what has more metallic character? Fluorine or sulfur? Yeah, they're both over here in the non-metals, but fluorine is up and to the right of sulfur. So sulfur has more metallic character. Okay. All right, so I'm going to leave it right there. That concludes this section. What we're going to do next is we're going to start off with those valence electrons, and we're going to start to draw pictures of molecules. We're going to draw them in 3 dimensions. And that's going to be a challenge for some students because learning to view things in 3 dimensions is not a function of how smart you are. It is a completely different ability in an individual's mind. It's more closely related to how that person is able to visualize and to be able to visualize in their mind. So the people who are better artists usually have an easier time with this because they can visualize in 3 dimensions better. People who are usually better at math that maybe struggle a little bit. And so we're going to draw some pictures. I'm going to build some models. I'm going to hold up the models in front of the camera and rotate them. So maybe you'll get a little bit better sense of what those shapes are. But ultimately, that's what we're going to do. And yep, and that'll be chapter 10. So see you guys all for now.